Today, let's talk about universal quantifier and existential quantifier. Universal quantifier can be viewed as the generalization of ant. When we talk about cats, we may say cat 1 has a tail, cat 2 has a tail, cat 3 has a tail, cat 4 has a tail, etc. We may only say that every cat has a tail. So universal quantifier can be viewed as a generalization of ant. Every cat has a tail. For any cat x, x has a tail. For any object x, if x is a cat, then x has a tail. These three sentences have the same meaning. When we see words like for any, for all, for every, for each, we know that they indicate the universal quantifier. Examples of statements with a universal quantifier. Example 1. The square of each real number is non-negative. Formally, we write for any real number x, x squared is greater than or equal to 0. More formally, we write for any object x, if x is a real number, then x squared is greater than or equal to 0. Example 2, which is a false statement. Every quadrilateral is a square. Formally, we write for any quadrilateral R is a square. More formally, we write for any R, if R is a quadrilateral, then R is a square. Statement form. A statement with a universal quantifier is a statement of the form for all x belonging to S, Qx, where S is a given set and Qx is a given predicate. More precisely, for all x, if x belongs to S, then Qx is true. Now let's talk about existential quantifier. Existential quantifier can be viewed as a generalization of all. So we may say people A have black hair, or people B have black hair, or people C or people D have a black hair, etc. So to be concise, we may say that some people have a black hair. There is at least one person with black hair. There exists some person X such that X has black hair. There exists some object X such that X is a person and X has black hair. These four sentences have the same meaning. When we see words like there exists some, there is or there are some, for some, there is at least one, we know that they indicate the existential quantifier. Examples of statements with an existential quantifier. Example 1. There is a prime number. Formally, we write there exists some integer x such that x is a prime number. More formally, we write there exists some object x such that x is an integer and x is a prime number. Example 2. The equation sin x equals to 0 with unknown x in the set of real numbers has at least one non-zero solution. Formally, we write there exists some x belongs to set of real numbers except 0 such that sin x equals to 0. More formally, we write there exists some object x such that x belongs to R excluding 0 and sin x is equal to 0. Statement form. A statement with an existential quantifier is a statement of the form there exists some x belonging to S such that Qx is true, where S is a given set and Qx is a given predicate. More precisely, there exists x such that x belongs to S and Qx is true. So we introduce an important concept which is called De Morgan's laws for quantifiers. The negation of for all x, Px is true is equivalent to there exists some x such that Px is false. We may understand the statement like this. P is not always true is equivalent to P is not true in some cases. Also, the negation of there exists x such that Px is true is equivalent to for all x, Px is false. We may understand it as no case can be found in which P is true is equivalent to P is always false. So let's do some proofs. The negation of for all x in S, QX is true is equivalent to the negation of for all x belongs to S implying QX is true. Here we just rephrase the statement. Here we use the material implication to change x belongs to S implies QX is true into the negation of x belongs to S or QX is true. And in this step, we will put the negation sign into the for all x. There exists some x such that negation of x belongs to S or QX. And then here we use the De Morgan's law again. There exists x such that x belongs to S and QX is false. Finally, we have this statement. Therefore, the negation of for all x belongs to S, QX is logically equivalent to there exists x in S such that QX is false. Similarly, for here, negation of there exists x in S such that QX is true, then we replace this statement to be the negation of there exists x such that x belongs to S and QX is true. We move the negation sign into the existential quantifier, and the existential quantifier is changed to universal quantifier. And then we have this statement. And then we distribute this negation sign into conjunction statement using the De Morgan's law. Then we will have this result. Using material implication, we will have this result. And finally, we have this result. Therefore, these two statements is logically equivalent. This is the end of the video. If you find my video interesting, please consider subscribing to my channel, like the video and comment down below. See you in the next